Hi, I'm Nard, and welcome to the first Levathia Brown devlogish thing. I've been working on this for a while, so we'll be going over some things I've already made, some technical demos, just having a little bit of fun. Levathia Bound is a 2D Metroidvania I've been working on for a while. For this devlog, I'll be going over my water system. It's kind of small and really inconsequential to the game, but it's a lot of fun and the techniques behind it are really interesting. So, to set the stage, I'd been passing by a bit of placeholder water for a while, and I decided I finally ought to do something with it. I made a little water animation, and it sucked. So I looked around at water I liked in other 2D pixel games, and I figured out two things. I wanted nice, big, long waves, and I wanted it to react to the player. So I took to my little Python playground to figure out how I wanted to do it. A little bit about how I use Python to prototype things. Python is a great language for these small tasks where a graph or a little text will work for output, particularly the graph part. With NumPy and PyPlot, I can easily graph and animate functions, like this. A little sneak peek of my end product in there. This way, everything runs fast and I don't have to worry about how I'll draw it in game. So, I started trying to make my water by using a sine function I could scroll through to make the base waves, and for the interaction splashes, well, that's actually about as far as I got. Try as I might, I couldn't find a nice function that resembled a splash. Propagating waves from a splash out, having them die down, having them interact well, I don't know that there's a closed form way of doing it. At that point, I remembered where all of these sine waves come from. The wave equation. This little differential equation. Don't be scared, I know it's a lot of weird math with a lot of weird symbols, and if you took a differential equations class in university or college, you probably hate to see these. But believe it or not, with our little friend, the finite difference method, we can turn this equation into a really nice algorithm to simulate wave height at fixed intervals. Okay, so dealing with our waves. Our wave equation here can be written in any number of dimensions, but we need just one. So, this weird d squared dt squared means second partial derivative in time, which you can think of as the acceleration of any given point on the wave, up or down. The d squared dx squared is the second partial derivative along the wave, which is basically the curvature along the wave. The c squared part is just the speed of the wave. Now, we can work with this in code by splitting our wave into a 1D grid. Instead of evaluating curvature, we estimate it by looking around ourselves on the grid and figuring it out. This is essentially the finite difference method. So, we'll get our estimate of this curvature by something called the central difference method of estimating derivatives. We can just look at a table and right there it is, the second derivative. This is the simplest estimate, the worst, but it'll probably work for us. From this, we can get our basic algorithm. Step 1, we calculate the acceleration, d squared u dt squared for each grid cell. We'll just apply the central difference method, and that's kind of interesting. At the edges, we'll have an issue. There's not a cell on both sides of the edge cell. I could look at properly solving this, called end conditions, if you want to look it up, but no, I think I'll just pretend the graph is exactly reflected and call one of the coefficients 2. It adds up anyway. So, step 2, going beyond there, we add the acceleration times delta time to the velocity for each grid cell. Yes, we keep track of velocity. Step 3, we add the velocity times delta time again to the cell's position for each grid cell. Now, it's important that we do all of these steps separately, as in separate loops. Something sneaky happens if you go straight to updating positions without preserving old positions. We start to calculate curvature off of a partially updated grid, and weird things happen. You start to have instabilities, which cause infinities. Very bad. We won't do that, but we'll implement it correctly, and nothing happens. That happens to be exactly what we wanted. To explain, we started the wave off in a neutral position, like the flat surface of an extremely still lake. Not exactly what we want in game, but a good start. So, to combat that extremely still lake problem, we'll add something we call in dynamics forcing. Every frame will get the wave a little push how we want it to go. I'll just use the sine wave for now, and there we go. But we didn't just recreate the sine wave we started with. It's a little bit different, but we can do a lot more with this. Let's write a little function to give the wave a spike at a predefined time. To not have to deal with the input in Python, I just want to make it look good. And there, the spike propagates. It might be a little sharp and weird looking, but that's because we gave it a really sharp spike. If we smooth it out, I'm sure it'll look better. At this point though, I'd rather be able to interact with it freely like we will in game, so I might as well take it there. At least I have a good idea of how to render it. The rendering is actually fairly easy. We'll simulate the wave on the CPU to facilitate interaction more easily. You can do it on the GPU if you'd like, but we're doing it on the CPU. After that, we'll upload the wave height in a texture that is 1 pixel high by the number of pixels the water is wide, packed into the range 0 to 1 to facilitate pixel stuff. We'll also need to tell the water shader just how large the water body is. With these 2 bits of information, we can reconstruct surface height on the shader and discard any pixel that's above it with the clip function. We just get the difference between where the current fragment is, which is a pixel, and the water level by subtracting the current pixel's y texture coordinate by the water level. We then apply a Sobel filter by utilizing the size of the water to figure out when we're right on the edge of the water, and we color that differently. That's it. That's the whole shader. It's in the description if you'd like to see it. Fairly easy. On simulation into Unity, and hey, it works. Ignore all the bug fixing I did between then and now. After a little playing with a graphing calculator, and yeah, I'm a massive nerd, I made a nice splash function to use for the interaction. It uses sine waves to have nice smoothness traits at the very ends. And, to boot, it's easy to scale up. We'll just wire that in and tie height and width of the splash to intensity, and after a little bit of work getting the parameters just right on the amount of splash to do, I think it looks great. But we can do a little bit better. We'll be going far past the original differential equation now. We can think of what we have set up here as a base. We've already added forcing to make little nice waves. We can add more forces too. To start, I want to make sure that the water always returns to a base level. Right now, it doesn't care if it's at a base level or 100 feet above it. So, to do this, we'll add a little force that pulls the water toward the middle, and we'll call it gravity. All it's doing is adding a little acceleration proportional to the height of the wave in a restoring direction. And that fixes that, but the waves still don't quite die down easily, do they? We can add another force too, damping, to act against velocity. Here, we're just subtracting for velocity proportionally to itself. Cranking this knob up can make the liquid feel more viscous. Nice, we can use that other places in the game. Finally, these sine waves that we're forcing with, they're kind of boring. We can use a little bit of purling noise to spice that up. We'll just replace the sine and add a little bit of it to the splashes, and that's not bad. And that's my whole wave system, actually. All of the relevant code is posted in the description. I hope you all have fun with it. Subscribe here or follow my Twitter to stay updated on the game. It's coming later this year.